Okay, we're going to take this green sheet, and this is going to go in our notebooks under removable or non-removable discontinuities. And so what we're going to do is when you look at a rational function, you want to try to decide which values could be excluded from the domain. Because whatever values will make the denominator equal to 0, we have to take out of the domain, and there's either going to be a vertical asymptote or a hole at that spot. Okay, so the first thing you want to do is you need to set the denominator equal to 0. Well, from what we did earlier in this year, when you have a trinomial like this, the easiest way to figure out the zeros is to factor it. So looking at this trinomial, we're going to factor it using the x method. Are there two numbers that multiply to get -2 and add to get -1? Notice that's -2 and 1. So we take those two numbers and we put them into our factors. So this factors into the quantity of x minus 2 times the quantity of x minus 1. Once you have your rational function in factored form, it's much easier to determine what values we need to exclude. So what value of x will make this 0? So that's at x equals 2. And what value of x would make this 0? That's at x equals -1. Now, because we don't have a factor of x minus 2 in the numerator, we cannot divide out or remove this factor. So since it's non-removable, that makes it a vertical asymptote. And the same thing here. Since x plus 1 cannot divide out with a common factor in the numerator, this is a vertical asymptote. That means that this graph is going to have a vertical asymptote at +2, a vertical asymptote at -1, and since the denominator is x squared, that means it's going to look something like this. And this middle chunk is going to go down like this. Now, if you notice in the directions, it says determine if each function is continuous. So we would say, no, this is not continuous because we have some breaks in it. If the function is not continuous, determine if the discontinuity is infinite or removable. So infinite discontinuity is another name for a vertical asymptote because this break goes forever all the way up whenever x equals -1, and this one goes forever whenever x is -2. Let's go to the next one. So the discontinuity is going to happen at x equals -1. And now we have to decide, can this be removed? It might be tempting to think that you can cancel an x and an x here, but x plus 1 is part of this factor. Sorry, x is part of the factor of x plus 1. So unless we have this entire expression up here, we cannot remove it. So since it cannot be canceled out, this would be a vertical asymptote. If you go down here, we're going to do the same thing. We need to factor the denominator. So two numbers that multiply to get -6 and add to get -3 would be x minus 3, x plus 2. And I'm going to put this in parentheses just so that you can clearly see this is where we can divide x plus 2 divided by x plus 2. We can divide out a common factor. And when we divide those out, that equals 1. So this simplifies to 1 over x minus 3. So before we divided these out, we have a discontinuity when x is 3, and we have a discontinuity at x equals -2. But since this one was able to kind of divide out of the problem, that's a removable discontinuity. So that makes the graph have just a hole at that spot, not an asymptote. Since the factor of x minus 3 remains in the denominator, that makes this a vertical asymptote. Okay, so let's go over here, or actually see if we can fit it in here. We're going to make a sketch of this. So at x equals 3, we're going to put a vertical asymptote.